This conference will now be recorded.
All right, this is the Day 2 Math 136 Review A for the final exam, and this is Part 2, starting with number 13. It says, given the function f of x equals negative x to the third times x minus 5 times x plus 3 squared, find all values of x such that f of x is greater than 0 and all values of x such that f of x is less than 0. Then sketch a graph of f of x. So this is the one we're doing a rough sketch of what the polynomial looks like. You can do this by a sign chart or by behaviors. A lot of us teach it by behaviors, so I'm going to go through that method. So when we look at this, it's going to be the two things we really care about are the end behavior, which means what is the polynomial doing as we get farther and farther away from 0, 0, towards the infinities on both sides. Are we going up forever or are we going down forever? And then the other thing we care about is our behavior at our zeros, which are our x-intercepts here. So for the end behavior, you need to know two things. You need to know the degree of the polynomial, and you need to know the sign of the leading coefficient. So the degree, if you're in a standard format, would be just the highest power that you see. But because this has already been pre-factored, we have to think, if I FOILed this all back out or distributed it all back out, what would be the highest power? And as long as all of your x's inside your parentheses are to the first power inside, you can just count up your powers on the outside. So this is 3 plus 1 plus 2, so that'd be 6. So if we were to multiply that whole polynomial back out, we should get x to the 6 coming out as the highest power. And that's an even degree. The leading coefficient is the sign of the number in front, so that's going to be negative. Now, the reason we care about these two things is because if you have an even degree function is its highest power, then that means your behavior at the end is going to be in the same direction, like x squared, essentially. They're either both going to be going up towards positive infinity, or the sides are both going to be going down to negative infinity. If you have an odd degree as your overall highest power, once it would be multiplied all back out, then you would be going in opposite directions, like x cubed. One side's going to negative infinity, the other side's going to positive infinity. So since we're even, we're going to be going in the same direction. And since we're negative, we behave like an x squared that's been flipped upside down. So both sides are going to negative infinity. Now the behavior at the zeros has to do with the x-intercepts for us. So if we set each of those guys equal to 0, we would get, I'm just going to write this here, 0, 5, and negative 3. So I like to write my zeros in a little chart, and I always do them in order from least to greatest. And then I'm going to talk about their multiplicities, which means how many times did each factor occur. And then that actually defines a specific behavior at that x-intercept. So the negative 3 came from the factor of x plus 3 squared. So that's got a multiplicity of 2 because it was 2 times. And when you have an even multiplicity, your behavior is that you are going to bounce at that point. Now, bounce is kind of not really a technical term. Touch sometimes is used in different books. It means that if you're above the x-axis, you'll touch that x-intercept, and then you go right back above the x-axis. You do not cross between positives and negatives. If you are at 0, we got a third power, so that's a multiplicity of 3. And I'm going to go ahead and write the other one down to 2. And x minus 5, we got the 5, and that had a multiplicity of 1. So when you have an odd multiplicity, you're going to do what's called cross, which means you actually cross between positives and negatives. The only difference is 1 is kind of a special case. At 1, you cross like a line. At any other odd power multiplicity, you're going to cross like x cubed, which means you kind of, and this is not just necessarily the direction it will be going, but you have that little flattening in the middle. Okay, so what we're going to do next is we're going to graph a number line. I don't worry about my y values. Until you get into calculus, you can't really figure out the max height and min at all of the values. So we're just doing a rough sketch of what's going on. And then we're going to place our x-intercepts on the graph first. So negative 3, 0, and 5. I put my end behavior down next because you base your behavior at the zeros off of what is going on from left to right, and that means you have to know the starting value that you're headed towards on that end behavior. So then in the middle here, we kind of follow our chart. This is why I put it in order from least to greatest. So at 2, we're supposed to bounce, which means since we're down, we're going to stay down. And then we eventually have to head back towards that next x-intercept, so we have to start going up again. At 3, we're supposed to cross like x cubed, so we kind of come in, flatten for a second, and keep going up. And then we have to eventually head back down towards that next x-intercept, and that crosses like a line, so mostly straight. Now, we don't know what the max and mins are of these little loops and humps and stuff are, and that's something you really can't figure out until calculus. So this is all we're wanting, just a rough sketch. The other piece that they did ask us for, and there'll be a blank for this if it is on your final, is that we want to know when the y values, because that's what f of x means, is bigger than 0, and when are the y values less than 0. That means when are we above the x-axis and when are we below. And you can just do this from left to right as you go. So from negative infinity to negative 3, our red part was below the x-axis, so that's less than. From negative 3 to 0, which is the next x-intercept, we're still below. From 0 to 5, we're above the x-axis. And from 5 to infinity, we're back below. Notice we are connecting all of these broken pieces by a union. Okay, that gets us to number 14. We're doing a long division problem. So, and the reason I know it's long division is, first of all, they asked for quotient and remainder, and we're dividing by something bigger than x to the first. If it was x to the first that you were dividing by, you could do synthetic or long division. But because this is x squared, we have to divide it by long division. So we're going to place the part we're dividing by on the outside, and I put a placeholder anytime I'm missing powers, so I put a 0x in there. Same thing inside, we're going to place this inside the function, and we have a missing x squared, so we need to put a placeholder for that. That just keeps everything lined up nice and neat by like terms, and it's also a skill that helps you when you get to synthetic division because you have to have zeros when something is missing. So the first question we want to ask is, what would you multiply 2x squared by to make 2x to the fourth? And we already have the 2, so it just looks like we need more x's. So we actually need x squared. Whatever you place on the top, you multiply it by everything out front. So this would be 2x to the fourth plus 0x to the third plus 6x squared. Now, when doing long division, you have to remember that we subtract to find our remainder. So we're going to end up changing all of those signs. So if you've done that correctly, that first term should cancel, and then you bring down everything else as you go across. Even these parts we didn't use yet. And this also tells me there should be only about 2 more rounds of division because I've placed this above its like terms. Now I want to ask, what do I multiply 2x squared by to make negative 8x to the third? 2 turning into negative 8, we would need to multiply by a negative 4. And we're turning x squared into x cubed, so we need another x. So now you need to multiply this negative 4x times everything out front. So that would make negative 8x cubed plus 0x squared minus 24x. Then we have to remember, and I always do this in a different color so you can see it, we have to go through and change all those signs. That's the subtraction step. That will make that cancel. This is negative 6x squared plus 36x minus 17. And then for our final round, we need to, and I know this is final because the x is finally matched. This is x squared and x squared. I need to ask, what do you multiply 2x squared by to make negative 6x squared? And that would be a negative 3. The signs do matter. So then we multiply that to everything in front, and that gives me the following. And then we change all of our signs to do our subtraction step. And that gives us a remainder now of 36x plus 1, because we cannot put 2x squared into something that doesn't even have an x squared. So our final answer is that our quotient is the top part, and our remainder is the final line where we could not divide even into that anymore. So there we go. Okay, for number 15, you're listing the potential rational zeros of a function. That is a list of possible zeros. It doesn't mean that they all are. In fact, sometimes none of them are. Say you could have a polynomial that all the answers are imaginary. So this is only just a possibility list, and there's a specific way we find it. In the Swakowski textbook, they call it the C's over D's. I know in some of the other pilots and stuff we have, you might have a book where they call it P's and Q's. It's the same concept. It's just semantics of what do you want to call it. But C stands for the constant term, and P or D stands, or Q or D stands for the leading coefficient. So this is the constant factors, This one is the leading coefficient. So you need factors of 36, and because it's a positive 36, that doesn't necessarily mean the two factors were positive. They could have both been negative. So since we don't know, we put plus or minus, and then we list all the factors of 36. So it's 1, 2, 3, 4, 6, 9, 12, 18, and 36. Then D is the leading coefficient, which is 4, and we list all the factors of 4, 1, 2, and 4. So the whole idea of the potential list of possible rational zeros is that you make all possible fractions out of all the C's over all the D's. We're not actually solving on this problem because they just said list. So my list is plus or minus, and then I'm going to make a list where I put each C over each individual D, and I just go across the whole C list that way. The only big thing is you have to make sure you don't list anything twice. Some people will want you to put them in order from least to greatest. Just depends on your instructor's preference there. I usually just make the list. So 1 over 1 is 1. 1 over 2 is a half. 1 over 4 is a fourth. So I've done all of the 1 over each of the D's. 2 over 1 is 2. 2 over 2 is 1. We've already got that. 2 over 4 is a half. We've already got that. 3 over 1. 3 over 2 is new. 3 over 4. 4 over 1. 4 over 2 is 2. 4 over 4 is 1. We've already got both of those. Then we want to do 6 over 1. 6 over 2 is 3. 6 over 4 is 3 halves. 9 over 1 is 9. 9 over 2 is new. 9 over 4 is new. 12 over 1. 12 over 2 is 6, which we already have. 12 over 4 is 3. We already have that. 18 over 1 is new. 18 over 2 is 9, which we already have. 18 over 4 it reduces to 9 halves, which we already have. And then 36 over 1, 36 over 2 is 18, 36 over 4 is 9. So this is the unique list of potential rational zeros. And that's the answer. So now number 16, it says find all of the solutions of the equation. And because this is non-factorable, when you look at this, you can see that there's 4 terms, but it does not factor nicely by factor by grouping. So our only possibility for trying to solve this is to try to use a P over Q or C over D list, whichever way you want to call it. And we start plugging those in to the function using synthetic division. Or factor remainder theorem, depending on which way you want to go with that. Some people would rather do those first, where you just plug it in and see if it equals 0 into the function, and then do the synthetic division. I usually just jump right into the synthetic division because that part has to be done to be able to factor it. So we need to list all of our C factors, which is 12. So C is plus or minus 1, 2, 3, 4, 6, and 12. D is 3, so that's the leading coefficient, so that is plus or minus 1 and 3. So our list would be all possible C's over D's, which is plus or minus 1, 1/3, 2, 2/3, 3, 3 over 3 is 1, 4, 4/3, 6, 6 over 3 is 2, 12, and 12 over 3 is 4. So this is our list, a little bit smaller than the last one. The best path that I usually tell students to go on is to try 1 and -1 first, because that kind of gives you an idea. First of all, sometimes those work and people will skip them. And it also gives you an idea maybe what to try next, because one of them might be closer to 0 than the other. So then if it's like, the positive number 1 is closer than -1, I'll go with +2 next. Just a little bit of kind of, process of elimination, trying to help me pick my next choice. So let's try +1 first. So remember, in synthetic division, you place all of the numbers, making sure no powers are missing of the x across a row. You pull down the very first coefficient, and then we start multiplying it by this number out front. We write it in the next column, and then we add. And we continue that pattern until we get to the end. The last box will have our remainder. What we're looking for is a remainder of 0, because that means that it factored evenly into that polynomial. So we could factor it, because remember, x, this is x equals 1, so that's a factor of x minus 1. So that could have been factored out. So 1 times 3 is 3. -4 plus 3 is -1. 1 times -1 is -1. -35 minus 1 is -36. 1 times -36 is -36. And when we add that together, you get -24. Okay, so that's our first one. That did not equal 0, by the way. Now we'll try -1. Bring down the same coefficients we had before from the equation. and we'll pull down the 3. Multiply, that's -3. Add, that's -7. Multiply, that's 7. Add, that's going to be -28. Multiply, that's 28. Add, and that is 40. So notice out of the two choices, and this doesn't mean for sure my sign is going to be a positive one, but this positive one is closer than -1 is to having a remainder of 0. So what I would probably try next is +2. So I'm going to bring my factors. And then I'm going to bring down the 3. So this is 6. Add that together, that's 2. That's 4. That's -31. That's going to be -62. That is -50. So that's even further away than what we started with. That typically says to me, maybe I should try a fraction, just kind of my goal here. So I'm going to try 1/3. I'm going to keep it positive because we know that the positive originally was closer to 0 than this negative one was. And again, this doesn't always get you there fast, but it's kind of just my method of plowing through these a little bit quicker, hopefully, and getting to a factor that works. There are sometimes more than one factor that'll work because all the factors could be nice answers. They don't all have to be imaginary or radicals, but we don't know that yet. So we pull down the 3. Now, when you multiply by a fraction, some people have trouble with this. Just multiply top times the bottom, or times the bottom number down here, and then divide by the denominator. So 1 times 3 is 3, divided by 3 is 1. Add the column. 1 times -3 is -3, divided by 3 would be -1. Add the column. 1 times -36 is -36, divided by 3 is -12. Bingo! We found something that gave us a remainder of 0. So what that means is we already know in our answer box, we would write the solution has 1/3 for sure as an answer because that worked. Now, because this was x to the 3rd power, you can immediately be done with synthetic division because now this will reduce 1 power, which means this is now x squared. So, and by the way, that factor out front is an x minus 1/3. We could make that look a little bit nicer, but this is essentially what we just did. We factored this guy out. And now we're going to solve just the second part. So you can set 3x squared minus 3x minus 36 equal to 0. And since this is quadratic, we should be able to solve it without using synthetic division. I would divide a 3 out first. As long as you do it to both sides, you're okay, just because that makes that a little bit easier to deal with. And it looks like this is factorable. So that would be an x minus 4 and an x plus 3 because it multiplies to -12 but adds to -1. So our other two solutions were integers. They were nice numbers. So -3 and 4 are also solutions. Okay. That gets us to number 17, which says find the vertical, horizontal, and oblique asymptotes, if any, of the rational function. So when you're trying to look for asymptotes, a lot of times it's best, essentially with anything we're doing with rational functions, to completely factor first. So the top is a monomial, so there's not much you can do there, but the bottom does factor into, let's see, factors of 20 that would make 12 would be 10 and 2 if they're both negative, and they would multiply to a positive then. So notice that doesn't cancel with anything on top, but your vertical asymptotes are anything that is in the denominator that does not cancel out. So we actually have two vertical asymptotes. To figure out the equation, because an asymptote is always an equation, you set it equal to 0 and move it over. So one of my vertical asymptotes is the vertical line x equals 2. The other one is going to be x equals 10. Now, you can only have either a horizontal or an oblique. You cannot have both at the same time. So essentially, the way you find out which one it is you're kind of doing long division. There's a shortcut as well, which I'll talk about. But you're asking yourself, if I wanted to divide this, I would ask, how many times does x squared go into 5x squared? And if the answer is just a number with no x involved, then that means you have a horizontal asymptote. If you say it goes in 3x times, that means you have an oblique asymptote, and you're going to have to do the long division to get the entire equation. But if you notice, x squared goes into 5x squared 5 times. So this is just a horizontal asymptote. Horizontal asymptotes are y equals the number. So if you have a horizontal, you don't have an oblique. Now, another way of doing this, and it's a shortcut method, is noticing the degree on top versus the degree on bottom. If the degrees match, then the leading coefficients are your asymptote, which is 5/1. So that is still y equals 5. If your degree on top is smaller, like say this had just been x to the first power, x squared cannot go into x. So that means you would have an asymptote of 0, which is still horizontal. The only time you get obliques is when the top power is higher than the bottom. And if that happens, you have to do the long division like we did in one of the previous problems to get the equation. Okay, so we're looking at number 18. We're going to sketch this rational function. So some things that we care about when we're sketching the rational function, we want to know the reduced function, which sometimes is the actual function if it doesn't factor and reduce. We want to know if it has any vertical asymptotes. We want to know if it has any x-intercepts, y-intercept. We want to know if it has a horizontal asymptote or an oblique asymptote. And we'll also want to know if it has any holes. Now, these may not always be listed in this specific order, but these are the things that we care about. This is already reduced. There's nothing you can factor out of that. So that x minus 4 is going to cause a vertical asymptote because it is something that doesn't cancel out of the bottom. So it would be x equals 4 if you solved it. That means that you have no holes, because holes only occur if a factor on top cancels with a factor on bottom, and it would create an open circled point at that position. So you have to solve for x and then plug it into the function to find the y, the reduced function, by the way. But we don't have a hole here because there was nothing in the bottom that canceled with anything on top. X-intercepts, after you've reduced your function, which we have, if you have an x on top, then you have an x-intercept. That factor that it would be attached to would cause an x-intercept. So we don't have any x's on top, so we're not going to cross the x-axis. The y-intercept you find by plugging in 0 for the x. So that's -3/4. So 0, -3/4. Make sure you write x-intercepts and y-intercepts and holes as ordered pairs. Now we're looking at, does it have a horizontal or an oblique? So this has no x on top, but an x on bottom. So that means if you try to do long division, x to the first can't go into 3. So that means the answer is 0. So that would be just a number. So it's y equals 0. That means we do not have an oblique. Okay, so what we're going to do is we're going to graph out what we at least know so far, and then we'll probably do a table of values or something to get some extra points, because usually you don't always have enough information. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm just making a grid with some points on it. That one didn't stay evenly spaced. Okay, so x equals 4 is a vertical asymptote. I'm going to do that in red and dash that in and label it. We have a horizontal asymptote at y equals 0, so I'm going to also dash that in. That's the x-axis, because that's where a y value would be a height of 0. And then we have 1 point, so 0, -0.75 essentially. So that's this. So that's not a lot to go off of. At least my assumption is that we're probably going to have a graph in this lower region. So when you're trying to figure out where is the graph and is it above or below the asymptote, what you do is you pick, if you have any x-intercepts and vertical asymptotes, you're going to pick points on each side of those two main features. So we didn't have any x-intercepts, but we did have a vertical asymptote at 4. So I want to pick points on each side of 4. And since I already have 1 point on the side of 4, I'm going to only pick 2 more. So maybe I'll pick 3 and maybe something negative, maybe -2, just to get a little bit further spread out of my points. And I'm going to pick 2 things bigger or 3 things bigger than 4. So maybe I'll do 5 and 8. I'm just kind of picking, a little bit further apart so that I can get an idea of what it's doing. So and we go back to our function, 3 over -2 minus 4 is 3 over -6, which is -1/2. Okay, 3 over 3 minus 4 is 3 over -1, so that's -3. 3 over 5 minus 4 is 3 over 1, so that's 3. And 3 over 8 minus 4 is 3 over 4, so that's 3/4. So let's plot those extra points. -2, 1/2, -1/2 I should say, 3, -3, 5, +3, 6, 7, 8 is at 3/4. So what you can see is it looks like our graph is staying in this lower region on the left side of the red line, and it's staying in an upper region on the right side of the red line. Now, the only way to know for sure that we don't cross the blue line, because vertical asymptotes are like, you cannot cross them. That is an undefined value. Horizontal asymptotes and obliques are sometimes like a fence you and your friend built. There might be a hole in it. You can slide through. So the only way to know for sure is to do a little equation. And again, we don't usually always check for this. It depends on your instructor if they've made you do this check every time. But you set the reduced function equal to your asymptote that was the one you're concerned about crossing, which is 0. And then you try to cross multiply and solve this. So that would be 3 equals 0 minus 0 again, so it's just 0. If there's an x left over in this equation and you can solve for that x, that means you cross the horizontal asymptote at that point. But since there's no x left, that means we don't cross. And even if there is an x left, if it cancels out while you're trying to solve, you don't cross. So I know now with some certainty that I'm not going to cross any of my asymptotes. So I can kind of just sketch this in as a nice rational function. All right, and the final problem on this review, number 19, find the inverse function of f of x equals 3x plus 4 over 2x minus 5. So an inverse function is just when you do opposite operations, essentially. You take an ordered pair that might be in a function. Let's say your ordered pair is 1, 5. You want to find a new function that goes from 5 to 1. And to be 1 to 1 is the only way you can have an inverse function. So if we're going to ask you for the inverse function, we're assuming that the function is 1 to 1. So the first thing I usually do is I write this as y equals 3x plus 4 over 2x minus 5. I like to write it as y instead of f of x because most people are more familiar with that as an ordered pair. Now, depending on your instructor, they may have had you swap the variables right now and then resolve for y, or they could have you solve for the x term and then swap the variables at the end. The main gist is that you're eventually going to swap x and y because that's what makes it the inverse. So I usually do it first. So I'm going to go ahead and do my swap, and I write it so that I know I did it. So I write this as the y's become x's and the x's become y's. Now to solve this, I'm going to cross multiply across my equal sign. So that's going to make 2xy minus 5x, because you want to distribute that to both, equals 3y plus 4. So technically, we already are looking at the inverse function. It's just not in function notation form yet. Function notation form requires the y to be by itself. And then we're going to call it f inverse of x. We're going to give it a new name. So I'm going to get all the y terms on the same side together by subtracting the 3y over to the left and adding the 5x over to the right. This is isolating the y variable on one side so that we can factor it out. So then we would pull the y out and we get 2x minus 3 in a parentheses equals 5x plus 4. The final step to getting this to y equals form is to divide by the 2x minus 3. Now, your final answer that you put in your box needs to have the function notation. So when you found your inverse function, we say it's f to the negative 1. It's not really an exponent, but it's f negative 1 of x, so f inverse of x, equals 5x plus 4 over 2x minus 3. Now, in classes, we usually went through what was the domain and range of these, but that's not followed up on this specific question. So I hope you enjoyed these videos. I hope they help you study for your final exam. I wish everyone the best of luck and have a great end to your semester and a great holiday season.